Hi, my name is Tanya, and I just graduated with a Master in Physics and Computational Physics.
And I'm Gabriel. I'm doing my master thesis in chemical engineering.
This summer, we participated in the Summer of HPC, a program offered by PRACE. The official title of our project is Neural Networks in Chemistry Search for Potential Drugs for COVID 19. The project is the application of neural networks in chemistry, more specifically to find potential drugs to act against the COVID 19 virus. We have been supervised by Dr. Marianne Gall and Dr. Mikhail Petoniak. In case you are interested in the topic, do not forget to check the final report and the blog posts published on the official Summer of HPC 2022 page that is linked in the description box below.
Finding new drugs is a very challenging task. The number of potential drug-like compounds is estimated to be up to a 9 decillion, which is 10 to the power of 60. Yet, the number of all compounds that have been synthesized so far is on the order of the hundreds of millions. Luckily, we have artificial intelligence to help us find better drug candidates.
In the project, the goal was to build neural network models to predict the docking score of the chemical compounds which can act as drug candidates for COVID 19. The docking score is a measure of the drug target interaction and therefore can be used to screen candidate compounds. In our study, the target used was the 3CL Pro SARS-CoV-2, which is a protein responsible for the coronavirus replication. The dataset we used in this project comes from the Buczynski et al. 2022 paper.
To be able to use neural networks for drug design, we employed molecular descriptors. These descriptors basically transform a molecular structure into a mathematical representation. Then, we use them as inputs for the neural networks. A descriptor needs some special properties such as translation and rotation invariance, because we know if we move or rotate a molecule in space, it is still the same molecule. There are different types of descriptors, and if you would like to learn more, check the articles linked in the description.
In this project, we used four different descriptors, namely the Coulomb matrix, the smooth overlap of atomic positions, atom-centered symmetric functions, and the many-body tensor representation. Each descriptor has its own set of parameters, hence our first step was to discover which set of parameters would result in the best model. These parameters, for example, impact the size of the descriptor vector.
The next step was tuning the hyperparameters of the neural networks. We tried different combinations of hyperparameters such as the number of layers, number of neurons in each layer, types of activation functions, and different optimizers. The combination that resulted in the least error was selected as the best set of parameters. In this table, we present all the hyperparameters that we evaluated. After training many models, these are the best set of parameters we found. Once we have already the best models, we can start predicting the desired properties of the molecules.
Here, we present you a plot of predicted values versus expected values obtained from the final training. The R-square obtained was 0.997 and the mean squared error was 0.03. As one can see, there is still some spread in the points and the model is not quite accurate. Even though this is not the best model, it still reasonably predicts the docking score. This brings a great perspective for this technique in the future. There were many possible combinations of parameters to tune, but due to lack of time, we couldn't investigate all the possibilities. For this reason, we believe that with further work, better models could be obtained. Do check our final report for more information.
We also wanted to investigate how parallelizing the script could speed up the creation of the descriptors. The creation of some descriptors was very time consuming, for instance the MBTR descriptor. To study the speedup, we created the descriptors using different number of CPUs. The plot on the right illustrates the speedup, which is the ratio of the time taken to create the descriptor using one CPU over n CPUs. As can be observed, the speedup for the Coulomb matrix and SOAP behaves as a constant. However, more number of processors could speed up the creation of the ACSF and MBTR descriptors. For these two, parallelization shows great advantage.
So here are the conclusions from our study. First, our model predicts a reasonably good docking score. However, even in our best model, there is a spread in the data. This is due to the fact that there are many parameters in both the neural networks and the descriptors which can be tuned. A possible solution could be to adapt to evolutionary computation. Furthermore, from the speedup curves, one can see that adding more processors can speed up the computation of complex descriptors such as atom-centered symmetric functions and many-body tensor representation, and result in accelerating this whole process of drug development. Such a study could be extended to other deadly diseases too, like cancer. It indeed is a very interesting branch of science and much work is needed.
So that's all from us. Thank you for your attention. Feel free to ask any question.